All right. So today we're in our last lecture. We're in chapter 10. When I say last lecture, I mean last new material lecture. Chapter 10, hypothesis testing. And today we're going to talk about error. So anytime you do anything ever in life, you could have an error, right? So same thing when we're looking at hypothesis testing. So we want to look at error, and specifically we're going to look at the level of significance, which is my alpha, right? And we're going to look at what we call a type 1 error and a type 2 error. Okay, and how, when those may occur. So of course, when completing hypothesis testing, there's always that possibility of an error occurring. So let's talk about this type 1 error first. So a type 1 error is if you decide to reject the null hypothesis and you have shown support for your goal or your alternative hypothesis, but it was a mistake. This is a type 1 error. So a type 1 error is a possibility, right? There's a possibility of a type 1 error occurring if you decide to reject the null. If you say, yes, I can reject my null, I do have support for my HA, but it was a mistake. We never know if it's an actual mistake. Like, we never know if we actually have an error. It's just we know that we have a possibility of an error, and it's the type 1 error when you decide to reject the null. The probability of this error occurring is alpha. Remember, alpha is also called the level of significance. And this is the probability of a type 1 error occurring. Okay, so that's alpha, our level of significance. So if our level of significance is 5%, then that means we have a 5% probability or a 5% chance of a type 1 error occurring. Now, I just mentioned, we never know if this happens. Well, how do we not know? Well, we're never actually going to study a full population, right? So we never actually really know that population mean or that population proportion. We never actually know those values. Remember, we're projecting what they might be based on our sample, right? That's inferential statistics. So we never know if we've made a mistake here, right? We never know if we rejected the null, but we shouldn't have. We never know if that's going to be true. It's just we know that we have a 5% or 1% or whatever alpha is chance of that error occurring. Okay. Then we have also what we call a type 2 error. This is if you decide that you cannot reject the null. And you did not show support for your alternative hypothesis, but it was a mistake. So meaning that you did not reject the null, right? We kept the null the same. We kept the center at the null, but we should not have. Again, we won't know if this is true or not. We won't know if we actually have this error. We just know that it's a possibility to have that error.
Professor?
Yeah.
So I'm reading, so it says if you decide you cannot reject the null and you did not show support for HA, but it was a mistake. So would the mistake be that you should have shown support?
Yeah.
Okay.
Yep. Yep.
I want to make sure I'm understanding correctly.
It's just means like a mistake happened someplace. Maybe the sample was like an unusual sample for your data. I mean, you know, there's different things that can happen, right? So it just means that you did not reject the null, but you probably should have. And like I said, we don't actually know if we ever make this mistake because we never actually know mu or p. It's just we know that there's a probability and there's a chance of that error actually occurring. And that's just what we call them, type 1 and type 2 errors. Yeah. And the probability of this one occurring is beta. Beta is new for us. We're not going to calculate beta, we're just going to talk about it. So beta is the probability of a type 2 error occurring. We're not going to calculate beta because it is a difficult calculation. I'm trying to show it all here. It's a difficult calculation, but what I am going to say is that alpha and beta are inversely related. Meaning as alpha decreases, beta increases. So that's what I mean when I say inversely related. So if alpha decreases, then that increases beta. So if I'm decreasing the probability of a type 1 error, then I'm increasing the probability of a type 2 error, which you could see how that could be, right? So, and then vice versa. Okay, I'll say, and the other way around. So if alpha increases, so our probability of making a type 1 error increases, then it's going to decrease the probability of making a type 2 error. Okay. So an example, type 1 error is like putting an innocent person in jail, right? So they're innocent, you've made a mistake, you put them in jail. But a type 2 error is like letting a guilty person free. So you made that mistake, you're letting them go and you shouldn't have. So that's kind of like what's going on. But so that's what we have. We have these two different types of errors and the probabilities go along with them. So you're going to notice on your team assignment today in part 3, there's it just asks you, okay, in the above questions, did you reject the null and then or did you not? And you're going to check a box and then you're going to say, what type of error could this possibly be? It's never something that you tack on to the end of a hypothesis test. It's always more like a follow-up question. So you might complete a full hypothesis test and you might see some follow-up questions about it. And that might be one of them. So it might just say, if an error was to occur, what type of error would it be? So just keep in mind, an error does not always occur, right? It's just the possibility of that error. Right? There's a possibility of error occurring in everything we do. Okay. So now I want to actually walk through a full hypothesis test with you guys. So let me write out this example. It's a little wordy. I'm going to try to get it in here. And then we'll walk through the whole test. And then hopefully we'll have time to work with our teams. So a study in 2011 found the average. Okay, right away, what type of data do you think this is? We have no context. Look what it says, average.
Numerical?
Numerical. I want you to think numerical when you see that word average. You don't even know what it's about yet, right? I want you to think. So I'm not gonna hold myself to numerical right away until I finish reading the problem, but I'm thinking right away when I see that word, numerical. Okay, and I want you guys to think that as well. So found that the average cell phone call length to be 1.78 minutes. A researcher thinks this is lower now. A random sample of 82 cell phone calls found a sample mean to be 1.65 and a sample standard deviation to be 0.35. Using a 5% level of significance, complete a full hypothesis test. Okay, so here's a problem that you guys might get, something like this. Guys, I want you to realize that anytime I ask you for a hypothesis test, it will say complete a full hypothesis test. This means I want all 5 steps. I want everything described to me. I want everything written out, okay? Every time I ask you. I will never ask you just for conclusion. The only time I would ever ask you for something like that is if I start the problem and I say complete the test. We would still be doing a full hypothesis test, okay? So keep that in mind. But in your homework, the homework might say, well, what is the test statistic? What's the p-value? What's your conclusion, right? That the homework's not gonna ask you for all of this, this 5 steps, like this full process. So keep that in mind, okay? All right, so let's get started with this. So we're going to start with this population step here. And with my population step, I have 4 parts, right? So the first one is the objects. I want to identify who we are studying. Now this is where I'm going to go to my sample, and it's what my sample's taken of. So a random sample of 82 cell phone calls. So right there it is. My objects are all cell phone calls. I feel like that makes it really simple. The next part is the variable. The variable is what's changing from cell phone call to cell phone call, right? So what are we studying? We're looking at the cell phone call length, right? So it's the length of the call. So you can write this different ways. I'm just gonna write call length, and you can write it any way you want. You could just say length, you could say length of cell phone calls. So you could be more specific or less specific, and it's okay in the variable. Especially when it's numerical, right? And we know this is numerical. First of all, we mentioned it in the beginning when we saw the word average. Then it talks about a cell phone call length. Length is a measurement, right? That's a meaningful number. I'm going to keep going and say, okay, well, it gives me an X bar. It's a sample mean, S, sample standard deviation. You only get those for a numerical problem. So I know for multiple reasons that this is numerical. So I'm going to put call length. I'm just going to put in minutes. Okay, and then I'm also going to put over here, this is numerical. So I like to note that, right? So if I know it's numerical, this is helping me all the way through the problem. So the next bullet point is going to be my unknown. And remember, the unknown, since it's numerical, is mu. You could always write this in as MU when you're typing up your work. That's completely fine. Do not use capital M. That stands for median. So we don't want to do that. Mu also can be found if you're in Word, and it's probably in other programs too under insert symbol. Anyways, I'm going to define mu now. Mu is the population mean. I always start it that way. And now I'm going to tie in the variable and the object. So I can word this a couple different ways. So I could say mu is the population mean cell phone call length. I could say mu is the population mean call length from cell phones. I could say it's the population mean length of cell phone calls. So I word it different ways. So I'm just going to put length of cell phone calls. I want you to realize this is your work, right? This is your paper. You write it how you want to write it, how it sounds good for you, okay? Then the last part is my goal. So remember, my goal is to show support for my HA, but I don't know what the HA is yet. So I am going to hold off on this and I will come back. Guys, don't let me forget to come back. Sometimes I forget. So I'm going to go over here to my method step. My method step, I want to write down my null hypothesis, my alternative hypothesis. I want to write what alpha is equal to and what curve I'm on. So I always start with the alternative hypothesis. Remember, this is what the researcher wants to prove. A researcher thinks that it's lower now. So lower than what? What we found in 2011, which is 1.78. So the researcher thinks it's less than 1.78. So that's what I'm going to put. So I have less than 1.78, but I need to know what is less than. It's my unknown, my mu. So mu is less than 1.78. Then my null is always exactly opposite. So mu is greater than or equal to 1.78. And of course, and I'm going to write it here, you could always write it as mu is equal to 1.78. I'm just going to put in parentheses. You don't need to write both, just write one. I just put it there in case someone likes to take this route. My alpha, that's my level of significance, and it said up here using a 5% level of significance. So 0.05 is 5%. And since we're looking at numerical data, we are on the T-curve. And remember, with the T-curve, I have degrees of freedom equals n-1 because that curve changes shape based on n-1. So now I can go back to that population step and write my goal, right? My goal is to support HA, which is that the mean is less than 1.78. So I can write this. So I want to show support to say that, now I already defined mu right up here, right? So I'm going to just write this down to say that the population mean length of cell phone calls, and I'm going to tack on my less than 1.78 is less than 1.78. And you can say minutes if you want. Okay, so there's my goal. So now my population step is done and my method step. Any questions on those first two steps? Okay, let's take a look at the next one, which is the sample step. This is the simple one, right? So I'm gonna try to, I can't show it all here. I can't. So we'll have to just keep referring back to this, okay? So my sample step, this is numerical, so I'm looking for N, X bar, S, and I'm going to check for normality. Sorry, you guys can't see what I'm writing. So N is the number in my sample, and it says that the researcher took a random sample of 82 cell phone calls. So right there, 82. The researcher found the sample mean to be 1.65 and the standard deviation to be 0.35. So this all came right from here. A random sample of 82 calls, X bar is 1.65, S is 0.35. Now I want to check for normality. This is where I'm always going to check N is greater than or equal to 30 first, and it is, it's 82. So I'm just going to say N is greater than or equal to 30. Yes, this is normal. And that's all I have to put for that. So that's the simple step, right? Okay, so now we're gonna move on to our fourth step. Remember, this fourth one is the results. This one's a little bit longer, and the results step just has a little bit more to it, even though it's still only 4 parts. So numerical data, I need to calculate the t-test statistic. Now guys, I want you to realize you have 2 ways of doing this. You can calculate the test statistic and the p-value separately, or going forward, you can use your calculator test function or your Minitab test function and do it that way. Remember those directions were on last week's, was it last week's? Yeah, I think it was last week's team assignment. So you can go either way. If you use the test function, what it does is it calculates the test statistic and the p-value for you and gives you the output all at once. I just happen to do it by hand myself most of the time. I just like it that way. It's probably because I'm a math person, but I want you to choose whichever way. So my test statistic is my X bar minus mu naught divided by standard error, which is S divided by the square root of N. I'm just going to plug all these values in. X bar is 1.65. Mu naught, that's the center of my curve. I need to go back and check, what is the center of my curve? The center of my curve, mu naught, is from the null, H naught, 1.78. That's the center of my curve. So 1.78 right here, divided by S, which is 0.35. And that is divided by the square root of N, not N minus 1. So it's 82 here. So when I do that calculation, I get negative 3.3634. Guys, when you see this, I want you to recognize that it's 3.3 standard errors away from the center. That's pretty far. I mean, I know it's not as far as like 31, like we saw in a past example, but I want you to know it's pretty far, right? 2 standard errors is far. So 3.3 is pretty far. So when I notice it's pretty far, I'm thinking that my probability that I calculate here in a minute is probably going to be small. I'm just thinking ahead. So before I move on to the probability, I want to interpret this value. So I'm going to say my X bar is 3.3634 standard errors below my center of 1.78. The reason why I say below is because it's negative. I don't need to include the negative here because I'm saying below. That's saying that it's negative. The next thing I want to do is I want to calculate the p-value. Remember what the p-value is. I'm calculating the probability. Let's draw a picture and see what we have going on, and it's going to help me with that calculation. So I have my picture. We're on the t-curve now, right? So the center of my t-curve is 0. My test statistic is negative 3.3. So right here, negative 3.3634. I'm calculating this area and this tail to the left. So now for my p-value, calculate the probability of getting a t-value less than negative 3.3634. Does everyone see that? First of all, the less than always matches my HA, less than here. But with the picture, you can just see it, right? It's to the left. It's smaller than that value. You're always calculating the area in that tail, and that area will be the p-value there. So when I do this, I'm looking at my TCDF because I'm on the T curve, right, for numerical. And here I'm going to plug in my lower bound. So I use negative infinity, which we know my calculator is negative 10,000 I use, up to my test statistic, which is negative 3.3634. Guys, just as a tip, if your test statistic is negative, it's always on the left, you're always doing less than. You're always going to do negative infinity up to that test statistic, that negative. If your test statistic comes out positive, you're on the right. Your test statistics, your lower bound, and then infinity is your upper bound. It's always the same thing, okay? Then here for TCDF, I need to put degrees of freedom, so 81, and I'm going to just write that down because we haven't looked at this a ton, so I'm going to write this, degrees of freedom equals n minus 1. So we know where that 81 came from because n was 82. So when I do this, I find my probability to be 0.00059. Now this one is pretty small, so you can call this very small if you want, or you can write the number. So I'll let you make that call on that one. So let's interpret this value. So if the population mean is 1.78, there is a 0.00059 probability of getting a sample mean at least as extreme as the one we got from sampling. There it is. There's the long step. All right, all done. Any questions on this result step? You guys all see how the picture is helpful? It's helpful for this. If you calculated the area over here, you're going to get a really large number, close to 1, right? Close to 100%. That would be incorrect. You're always calculating the area in the tail. It's always going to be a small number. Whew, excuse me, sorry. I felt that coming. All right, guys, let's take a look at the conclusion. So now the conclusion, I have to use what I just found up here, right? The first thing I'm going to ask myself is the p-value less than or equal to my alpha? So is 0.00059 less than or equal to alpha? We stated was 5%, 0.05. The answer is yes, it is less. So we can reject our null. The idea behind this, if I say I can reject my null, then I'm saying that I don't think the population mean is 1.78, like I stated here. When I reject my null is that it equals 1.78. I'm rejecting that idea. I'm saying I don't think it's that because I have support that it's whatever we're studying, which in this case is less than, okay? So if you say you reject the null, you're saying, I don't think that the mean is 1.78. I think it's less than. If you cannot reject the null, then that means you're kind of accepting that idea that maybe it is 1.78. Maybe the center of my curve is 1.78 minutes, right? Maybe that population mean is 1.78. I just like to kind of mention that. I had someone ask me that before, and I like to remember questions and go over those. I'm going to make my conclusion statement next. So at the 5% level of significance, our sample, now since I've answered yes, I'm going to say does show support. Now I'm just going to write my goal here. I'm going to go back and find my goal, wherever it may be, all the way here. I'm going to write it, this whole thing right here. It does show support to say that the population mean length of cell phone calls is less than 1.78 minutes. So what I'm saying is that I'm rejecting that it is equal to 1.78, and I'm saying that I'm showing support that it's smaller than 1.78. Sorry guys, I don't know why I'm like sneezing all of a sudden. I'm allergic to something all of a sudden here. Okay. Now, I want you to realize that there may be a follow-up question, but there's not always a follow-up question. So it would be completely separate. I never want you to tack on anything automatically about a possible error. You wait for it to be asked. So the question could say, is there, like, if an error was to occur, which one could it be? You never want to say, oh, a type 1 error or a type 2 error happens. No, it's the possibility that one of those errors could happen, right? So which one could it be here? Well, remember, for a type 1 error is if you reject the null. A type 2 error is when you do not reject the null. So here I've said that I've rejected the null. So the idea here is that it's a possible type 1 error. So possibly a type 1 error could occur, okay? And it's always a follow-up. This is never just something you tack on. I want you to know that. You will be asked this if I'm wondering, okay, about the error. It's never just something you tack on to the bottom of your conclusion. This is like separate, okay?